Okay, so before we start the last topic for the week, topic four, okay, let's just take a look at the big ideas we're going to try and pull out. Okay, so we're going to look now at how do we actually measure earthquakes, quantify them, put a value to them. Okay, so the things I want you to look for today, how do you find the Richter magnitude? For every difference of one on the Richter scale, how much larger are the waves? Okay, and for every difference of one on the Richter scale, how much more energy is released? Okay, so last time we talked about locating an earthquake, right? But you got to remember, okay, knowing where an earthquake is very important, obviously. It helps us prepare, but sometimes we're not going to need to worry, right? A lot of the times you hear about earthquakes that people don't even actually feel, right? Or ones that, yeah, you feel, but nothing too major, right? Your paintings maybe shake a bit, but no need to worry or evacuate. So it's also important, right? If I, again, to go back to the spider, if you come into my room and I say, okay, there's a spider in here, it's right over there, your other question is going to be, well, is this a man eating tarantula or is this a little harmless daddy longlegs, right? So it is important to know not only where the earthquake is, but how big of a deal it is, right? So we've come up with a method to communicate the severity of an earthquake, how kind of serious it is, okay? And so what that is the Richter scale. You may have heard of this before, okay? So a Richter scale is actually a really clever scale. It allows us to put a number to the magnitude of the earthquake, no matter how far away it is from us. So it measures total amount of energy released, no matter how close the station is to it. So again, we take the largest wave produced by an earthquake. So you can imagine bigger earthquake, bigger waves, right? Bigger shaking of that seismograph. Okay. Then, like we talked about last time, we calculate the distance from the epicenter to the seismograph using our SP time interval. Okay. Those are actually the only two things we need to know to figure out this thing's Richter rating. So think about it. You've got to measure how much it shook you and how far away it is. You can imagine a really, really, really big earthquake, if it's far away enough, it's still not going to shake you that much, right? And then on the flip side, a really small earthquake, if it's close to you, it could still cause some pretty big shaking, right? So we have to come up with a scale that doesn't mess with that. If it's close to us, we can't call it a 10.0 earthquake just because we shook a lot, right? If we get a little nudge, we can't send the world into panic by saying, oh, there's a huge earthquake coming, right? It might have been huge for us just because we were really close to it. And on the flip side, we can't say, oh, this earthquake's nothing to worry about, but it was halfway across the world and it actually was really big. And the fact that we felt anything at all means it was huge, right? And the fact that they made it that far. So essentially, there's a scale kind of made up for us. We just plot the two on their scales shown below. So down here we have on this one, we put the SP time and then that tells us the distance away. So we just draw a dot when we figured out the SP time, okay? And over here, amplitude just means how big the wave is, how big the biggest wave is. So based on where we are, we put a dot at what we measured our SP time to be, and then we put a dot at where we measured our largest wave to be. So you can see they've actually used the data here, right? So their SP time was 24 seconds. That's the gap between the P waves arriving and the bigger S waves arriving. So they measure that to be 24 seconds. So they put a dot here on the 24 seconds, right? There's 20, there's 30, 24 is about halfway between. And then they said, okay, so it was this far away. We go over here and say, well, how big were the waves? And so you see they've measured the biggest wave there, right? They measured the amplitude of that wave to be 23 millimeters. So they went on this one. They said, okay, 20, a little bit above that, 23. And then they just took a ruler and drew a straight line across. And that tells us the Richter magnitude. Okay. Where they intersect, where the line crosses the magnitude scale, is the Richter number or the Richter rating. So what is the magnitude, the Richter rating of this earthquake? It is 5.0. We would say it has a 5.0 Richter rating. Now, again, remember the cool thing about this scale is that it works no matter where you are. A 5.0 is a 5.0 is a 5.0. So what I mean by that is, what if we were closer to the earthquake? We'll pretend if we were closer to the earthquake, the distance wouldn't be as far and the SP time wouldn't be as far. So maybe we would be down there, right? Maybe that's what the distance would be that we calculated. Well, if we were closer, would we feel bigger shakes, bigger waves up here, or would the waves be smaller down here? Well, they would get bigger, right? And we would feel maybe that level of shaking. And so the cool thing is when you draw a straight line, it doesn't matter because look, it gets corrected for by the Richter scale. So either way, you get a 5.0. Now, what if you said, these shakes weren't that big? I don't know why everyone's calling this a 5.0. We only got waves that were this big. We only got 5 milliliter waves. Remember, the Richter scale works either way. If you are getting smaller waves, are you closer or are you farther away? If you're not getting shaken as much by the earthquake, well, you must be farther away, right? So your SP time, since you're farther away, would be bigger. And then if we went to connect, we would say, okay, I guess, yeah, the Richter scale works. It doesn't matter where you are. You kind of always end up intersecting at 5, okay? So see what I mean? It works. No matter where you are on Earth, you get the same Richter rating. So red is farther. And since it's farther, they get smaller waves. They don't shake as much. Okay, blue is what happens if you're closer. And so you got bigger waves, right? But again, the way the Richter scale works, it's pretty ingenious. It works so that it doesn't matter. You should always get the same Richter rating. Okay? Either way, still get rating of 5.0. Okay, so let's just do some practice. Let's determine the Richter magnitude for this earthquake. So this is data from 3 seismograph stations. Okay, so they measured their SP time interval, and then they used that. That's the gap between the P waves and the S waves arriving, right? Again, that's like counting the seconds between thunder and lightning. And they use that to calculate this distance. So they're telling us the distance to the epicenter at station A is 200 kilometers. So let's just do some color coding here. Let's make station A, we'll do in red, station B, we'll do in blue, and station C, we'll do in green. Okay, so station A, they calculated they were 200 kilometers away. So I go to my distance scale and I say, okay, 200 kilometers and red for station A. Then at station A, the biggest waves they got were 22 millimeters. So 20, just above 20 is 22. So 20 on the amplitude scale, okay? Just a quick kind of question here for you. Which one do you think is closest to the earthquake? Station A, station B, or station C? Well, who got the most shook, right? Who got shook the most by the earthquake? Station A had waves this size, 22 millimeter waves. That's like, right? Versus station B, which did not have as big of waves, or station C. So station A is probably the closest, right? So station A must be the closest. We can think of it that way. Whoever's closest is going to get the most shook. But don't forget over here, right? SP time interval is basically a way of saying how far away are you from it. Of course, the distance is actually here, right? So you could just use that too. But the shorter the SP interval, the closer you are to the earthquake. Okay. Back to it. Station B, their SP time interval was 30 seconds, which they calculated to mean they were 260 kilometers away from the epicenter. So there's 200, there's 300. A little more than halfway would be 260. Okay. Now we have to figure out, okay, so they were a little further, which means their waves should be a little bit smaller. And yes, they were. They were at 15. So there's 10, there's 20. So 15 is right in the middle. Okay. Station C, okay. Their SP time interval was 40, so they were further away. They calculated the distance to be 360, so there's 300, there's 400, 350 would be the middle, so a little bit above that. And the minimum amplitude of their S waves was the maximum. So the maximum amplitude of their S waves was 7 millimeters. So there's 2, there's 5, so 7 would be closer to 5, but almost halfway. Okay, so realistically, I should have been connecting them as I went, but this will be satisfying if we kind of do it all at the end here too, okay? Now, what do we know about the Richter rating? No matter where you are, if you're at station A, station B, or station C, you should get the same Richter rating, okay? So let's try this one out. If we are at station A, red, so we're going to connect the dots for station A, the red dots, okay? And if you're at station A, that's what I'm getting. Technically, that is enough, right? Technically, since we should anyway get the same rating no matter where we are, we can now say this has a rating of 5.0. But it never hurts to ask other stations what they calculated, and then you can corroborate your data, right? It's like doing an assignment with a friend and saying, hey, what'd you get? And if you both got the same answer, then yeah, you probably did it right. Okay, so let's connect station B. Where do they intersect the Richter line? Aha, look at that. The exact same place, pretty much, right? Well, not pretty much, the exact same place. Let's look at the green one. Where does it cross the middle line? Station C. Aha, look at that. They all cross at the same place, okay? So they all cross at 5.0, just like the last one. So what's the Richter magnitude of this earthquake? It's roughly 5.0. Okay. Now the thing about the Richter scale is, you might be thinking, okay, a 2.0 is a little worse than a 1.0, okay? And a 3.0 is a little worse than a 2.0, which is a little worse than a 1.0. The Richter scale actually doesn't work that way. It's a logarithmic scale, okay? You'll learn about those in Math 30. What a logarithm basically is I think of it as a way of counting in a times 10-y sort of way. So what I mean by that is you can count in a plus 1-y sort of way, right? You add 1 every time. 1, 2, 3, 4. That's counting in a plus 1-y sort of way. Count in a plus 2 sort of way. 2, 4, 6, 8, right? You can do that. You could even count in a times 2 sort of way. That would be timesing by 2 every time. So 2, 4, 8, 16, right? Doubling every time. Logarithmic scales are counting in a times 10 sort of way. What that means is that an increase by one whole number on the Richter scale means that the waves that are arriving are 10 times larger. So a 2.0 earthquake is not going to be a little bit bigger. It's not even going to be double what a 1.0 earthquake was. It's going to be 10 times larger waves. Okay. That means that a 3.0 earthquake compared to a 1.0 earthquake, that's a difference of 2. So it's going to be 10 times 10, right? A 3.0 is 10 times worse than a 2.0, which is 10 times worse than a 1.0. So it's 10 times 10, 100 times larger waves. A 3.0 earthquake has 100 times larger waves than a 1.0 earthquake. And that's not even where the craziness ends. An increase of 10 times the wave height actually means 30 times more energy is released. Okay. So when you're comparing the earthquakes based on how much energy is released, you don't go times 10 times 10 times 10 for every difference. You go 30 times 30 times 30 for every difference. So the example they give here, right, is the same one I give. A magnitude 2.0 earthquake has waves that are 10 times larger than a magnitude 1.0 earthquake. And the 2.0 earthquake releases 30 times more energy than the 1.0 earthquake. Okay, so just some practice with this. We're going to compare them based on both wave amplitude. So to get wave amplitude, we times by 10 for every difference of 1. Okay, for energy, we're going to times by 30 for every difference of 1. So for a 7.0 and a 5.0 earthquake, how much worse is a 7.0? How much bigger are the waves? Well, first let's just figure out, okay, well, 7 minus 5 equals 2. Okay, that's going to be important. So 7 minus 5 equals 2. So there's a difference of 2. That means we'll do a wave amplitude in blue. So for waves, okay, for wave amplitude, we're going to have 10 times 10. Why 10 times 10 twice? Because there's a difference of 2. So 10 times 10 equals 100 times larger. Okay. What about for energy? We're going to do the same idea, but with 30 instead of 10. So 30 times 30 equals 900. 900 times more energy released. Okay. Now you might be noticing, hey, 10 times 10, that's 10 to the power of 2, right? And you're right, 10 to the power of 2. Or 30 times 30, that's 30 to the power of 2. Okay. So that is actually what we're going to be doing. We're going to figure out the difference, and then we're going to, you can do if you want, like if you figure out the difference is 3, you can go 10 times 10 times 10, or you can do 10 to the power of 3, okay? 10 to the power of whatever the difference is, and then 30 to the power of whatever the difference is for energy. So if we compare a 4.0 earthquake and a 1.0 earthquake, that's exactly what we're going to have to do, right? 4 minus 1 equals 3. So for wave amplitude, we could do 10 times 10 times 10 equals 1,000 times larger waves, okay? Or we could also do, or 10 to the power of 3, because that's what we got our difference to be. Either way, we get the same answer, okay? Two ways of doing the same thing. Now, when we go to do energy, okay, we could do 30 times 30 times 30 equals 27,000 times more energy in a 4.0 compared to a 1.0, or again, 30 to the power of 3, because that's the difference. So 27,000 times more energy in a 4.0 than in a 3.0. What about a 5.6 and a 1.6? You might be looking at those decimals and going, yeah, I don't want to deal with those. Not so bad, right? 5.6 and 1.6, that's still just a difference of 4, right? If you take 5.6 minus 1.6, that just still equals 4, okay? So what do we have to do? You guessed it, 10 times 10 times 10 times 10. Or we could just say 10 to the power of 4 equals 10,000 times larger waves in the 5.6 quake, okay? What about for energy? Same idea, except instead of 10s, we use 30s. So 30 times 30 times 30 times 30, or 30 to the power of 4 equals 810,000 times more energy released. See what I mean? A 5.6 doesn't sound that different compared to a 1.6. I mean, it obviously sounds worse, but there's not a scale of 1 to 10, right? It doesn't work like that. It's 810,000 times more energy. It's way bigger. A 1.6 is nothing. You wouldn't even notice it. A 5.6 could be pretty damaging. Okay, and then finally an 8.2 and a 2.2. Oh my gosh. So 8.2, don't get freaked out by the decimal. 8.2 minus 2.2 equals 6. So again, you could do 10 times 10 times 10 times 10 times 10 times 10. You can punch that in your calculator. That would work. Or you could do 10 to the power of 6. Just saves you a little bit of time. It's the same thing, right? So 10 to the power of 6 equals 1 million times larger waves. So the waves will be 1 million times bigger in an 8.2 earthquake than in a 2.2 earthquake. I'd say so, because an 8.2 earthquake is devastating. A 2.2 earthquake, you might barely feel. Now, you thought that was big. Think about the energy now. So now we're going to do not 10 to the power of 6, 30 to the power of 6. You're going to get 729 million times more energy released, okay? So a logarithmic scale, it grows quickly, okay? It's not as simple as saying, oh, 6.0 is pretty bad and a 5.0 is a little bit better and a 4.0 is a little bit better than that. No, right? We're talking about times 10 times 10, or even in the case of energy, times 30 times 30 times 30. So if you're kind of wondering what these numbers mean, you want to put some context to it, I'll let you just kind of read through this table. I don't think I'll bother going through and saying it because it's all right there for you to read anyway. Okay, but you can kind of get an idea. Less than 2.0, people aren't even really going to feel it. 8,000 of them happen every day, right? As we go up, it gets a lot worse at each step because, again, each one has 10 times bigger waves and releases 30 times more energy. So when we get up to the 10.0s, there's actually never even been one recorded of that size. It released the same amount of energy as a 24-kilometer meteor hitting Earth, right? So I'll let you read through that table to kind of contextualize the numbers on your own. Here's another way to just kind of put it into perspective. Some comparisons here on the left side are the earthquakes, and here on the right side are things you could compare them to, okay, in terms of the amount of energy released and the equivalent kilograms of TNT going off, right? Even a 2.0 earthquake is the equivalent of 56 kilograms of TNT going off. Of course, 56 kilograms of TNT going off is a lot of energy being released. It's just that if it happens on the other side of the world, you probably wouldn't notice. Once we get up to these numbers, yeah, you're probably going to notice, okay? So you can look at some of the stuff on here, right? Things like the world's largest nuclear test ever, still less energy released than even a 8.0 earthquake, okay? So these things are serious. There's a lot of energy involved here as that builds up, and it's just like the rulers slapping, only on a way bigger scale, right? So when I was talking about that before, and I said, hey, you know that built up energy can hurt if your friend has ever been a jerk and slapped you with their ruler, right? From that little thing, a lot of energy. imagine if it wasn't a little thing, it was the tectonic plates of the earth. And now you're realizing how much energy there is in an earthquake. Okay, so I'll throw these back up to wrap up. But that wraps up topic 4. So how do you find the Richter magnitude? Literally, what do you have to do if you're given the scalings? Okay, for every difference of 1 on the Richter scale, how much larger are the waves? And for every difference of 1 on the Richter scale, how much more energy is released? Okay, also, how do you find the differences? So you should be able to actually do the math too. Okay, so that wraps up topic 4 and this week's kind of stuff for the offsite learning. So if you're looking for practice for this stuff, go try that in the formative work. And then if you're feeling comfortable with the whole week, go ahead and you can do the summative Google form for this week. Please do come into Flex or just send me an email or whatever you want to do if you're having any questions, okay? Have a great weekend. I'll see you next week.